Well, today I'm going to cover some material from section 4.9. This video will be the last one that we do anything in chapter 4. So on Wednesday we'll start looking at some material in section 5. I think. Wait. Oh right, I made an actual schedule, so this is probably something I want to share with you guys. Yes, 5.1 will be the thing for Wednesday. April Fool's Day, but this won't be April Fool's. We'll really be doing stuff. So today we're going to do a little bit of an intro to graph theory, and I'm going to use Sage for that. This is something that I think I had asked everybody to, this is something I'd asked everybody to do previously, to create a free account on CoCalc so that you can use Sage on their cloud service. We're going to particularly look at some of the Sage commands involving graph theory, but it's a generalized programming language. In fact, it's sort of a superset of Python. So if everybody knows Python, that kind of code works fine in here. There's additional commands that are written, actually themselves are written in Python, and you can look at the source code for those commands. But well, what I generally recommend is we want to first. I'm going to teach you a little bit about how to use this interface, and then we'll go on to do a bit more about graph theory. So the first thing is there's these little dividers between sections of this notebook. If you click on the divider, you'll get a new section. So if you need to create a new section to do some computations in, that's fine. If you just backspace out of it, or is there a way to kill it? Anyway, a question mark after the name of a command will get you help on that thing. Sometimes this help is a little obtuse, and it just skipped me down to the edge of the screen. Okay. So what I normally do is, to be honest, I normally drop right down to where I start seeing examples of how they use the command. Right, so here's some examples, and then I copy that, and then usually try to take a working example and then modify it to fit my needs. You can show or hide a section by clicking the little triangle. So I just got rid of that output from the help command. If you want to go look at that, it's certainly instructive. Here's our first example of creating a graph. So there's a graphs constructor here, graphs, and another little piece of how to use the interface help. Why is it jumping to the edge of the line, end of the line when I do something? If you, sorry, let me work in here. If you want to find out what the member functions of an object are, you can put the dot that goes after that, like that constructor, and then hit a tab, and it'll give you an entire huge, in this case, list of all the possible things that you can do. This is basically an enormous list of graphs that have that are known to people. Some of them are a little odd, like there's the map of Africa, but there's more well understood graphs that have names. I've, for instance, played with Clebsch graphs before, complete bipartite graphs. I will actually show you some of those later. The one I want to look at right now, though, is a complete graph constructor. Okay. Well, I already did that in the next cell, so let me jump to that. Notice that this cell has things happening on two different lines. You hit enter if you are editing and want to create something that shows up on two different lines. If you want them to be just on the same line, you can do that too. Just separate commands with a semicolon. Okay. I'm gonna go ahead and leave them on two separate lines. Notice that means I've used the return key, the enter key, to do the editing of the the visual layout of this thing. How do I get it to actually run? Well, there is a go button somewhere up here, but I usually use the keyboard shortcut, which is to hold down shift while you hit enter. Okay, so that created a layout. This is a little big. Back away. So that created a layout, and this is called a complete graph because, well, look, it's got 4 edges in it. That's the argument that I gave to the constructor. Complete graph with a 4 after it right there. But it has also every single connection between those dots that you could make, right? Well, modulo the idea that we're only allowed to have one connection. So, but this is how you should think about a graph. It's a bunch of dots, and the terminology is the dots are called vertices, and there's line-like things that go between them. This layout may give you the mistaken impression that those lines are always straight lines. They don't have to be. They can be sort of arbitrary curves. But they begin and end at a vertex. Okay. This is going to be essentially the same graph, but I wanted to show it to you because it gives a way to, it shows you a way to implement constructing a sort of generic graph. So what is this argument to the graph constructor there? Capital graph is also a graph constructor, but that's a dictionary. Now, if I'm expecting that most of you will have used dictionaries before, but if you haven't, you should think of a dictionary as kind of a list, where instead of giving an index into a position in the list, you give a name for a position in the list. So this has a list with a 0th entry, a first entry, and a second entry. And those entries have subdictionaries associated with them. So this one literally is a dictionary of dictionaries. The dictionary associated with item 0 includes items 1, 2, and 3, and those things have associated with them labels, A, B, and C. The things associated with item 1 in the list was another dictionary with things named 2 and 3, and those have labels D and E. And finally, well, how is this working? What this tells me is that 0 is hooked to 1, and that hookup is labeled A. Also, 0 is hooked to 2, and that hookup is labeled B, and so on. So we've got actually every connection between 0, 1, 2, 3, and they're labeled A, B, C, D, E, F. So let me run this code by hitting Shift and Enter, and it'll show it to me. So this is one version of a layout. This is a particularly unhelpful one because it's just a static print. It's also unhelpful in the sense that one of the labels is right underneath one of the other labels. I think this B was the label between 0 and 2. But the label between 1 and 3 would have been D, and it's no, 1 and 3 was labeled E, and yeah, that label is underneath the B there. A different layout can be achieved by changing the way you call this, and I don't know if this is a bug or a feature, but you can say show G1. That is, give the graph that's being shown as an argument to the show function rather than... And then you get this cool little springy graph. Right? Now this is a little hard to see because the default layout is so tiny, and I wasn't able to figure out how to change the defaults on this at all. So, but you can see that the dots are labeled 0, 1, 2, and 3. And then the edges between them have the labels A, B, C, D. See how the C and D ended up almost on top of one another? That's what happens when you try to do automated layout of things like this. Okay, so what's next? I just think this is cool. You can also run a show function that treats things as three-dimensional, and in that case our graph is kind of a little triangular pyramid. That's what well, the graph's called K4, actually, that we just did, the complete graph on 4 nodes. But I'm mostly showing you this stuff just so you'll have an intuitive sense of what a graph is about. What does a graph mean? Wow, here's another another kind of graph, but notice this keyword, multi-edges, and I've set it equal to true. Sometimes it makes sense for there to be multiple connections between the vertices of a graph. The things that are represented might mean things where you could be connected in multiple ways. For instance, there's a famous graph that is called a collaboration graph. There's a silly game called 4 degrees of Kevin Bacon, 5 degrees, I forget what it's called now, but it asks you to hook up two movie stars based on whether they've been in a movie together. So, and the eventual goal is to hook your way back through various stars until you get to Kevin Bacon. So, and I don't know enough movie trivia to be able to play this game well at all, but the point I was going to raise is that there's certainly pairs of movie stars who've been in multiple movies together, so they would have multiple connections in that graph. There's other things where multiple connections don't make sense, like airlines, for instance, are very interested in a graph where one collection of nodes are pilots that they have in their employ, and another collection of nodes is aircraft that those pilots may or may not be qualified to fly. And you put a connection between the pairs if pilot X can fly airplane Y. Now, he can either fly or he can't fly, so there having multiple connections wouldn't make sense. But the graph I'm about to show here would be for a scenario where indeed you can have multiple connections, and that's why multi-edges is true. Notice how the dictionary has changed. The connections between 0 and 1 have after it a list of labels. So now that'll also show in spring layout. It's kind of funky looking the way it's laid out this way. I'm going to try to pop it over so it looks the normal way. This is a very famous graph, so there's a sort of normal way that this thing is supposed to look. So let me show you that. This is, let's see, page 678 in the book, several chapters ahead of where we currently are, but it shows the origin of graph theory, and it started because of a silly puzzle that people in this medieval city, well, I guess not really medieval, it was the early 1700s when this puzzle was proposed, so Renaissance era actually, but in any case, the village had been there since medieval times, and it even had bridges in place which were built by the Romans. So this village was called Königsberg, and just to make things a little clearer, there's a kind of a line drawing of how that village or that town looked at the time, 1736, when this guy underneath, Leonard Euler, was able to solve their puzzle. But anyway, here's the layout. There's an island, there's a north bank and a south bank of the river, and then off to the east there are two different branches of the river. So basically these two branches of the river are coming together, flowing around that island and heading out to the sea. Königsberg, that literally is the king's town, or the king's city, was a part of, well, I guess it's not quite fair to call it Germany because it wasn't known as Germany yet, but it was definitely under the influence of the Germans. Anyway, actually Prussians at the time. The city had 7 bridges, so you can see these little gray blocks that are. Let me try to zoom a little bit. These gray blocks represent the Roman bridges, and there were 2 between the island and each of the banks of the river. And so you see that's a scenario where it makes sense to have multiple connections. I mean, there's a landmass to the north and there's this island, and they can be connected once or more than once. It's not a problem. Anyway, there's also this promontory over here that's labeled C, and there's a bridge from the island to the promontory. There's a bridge from the promontory to the north bank and to the south bank. They put bridges everywhere so you could get around and visit the different parts of this town. Now, the puzzle that apparently the townspeople came up with on their own was this sort of question about taking a walk. Could you start at any point in the village and walk across the bridges and end up covering them all exactly once. So never have to retrace your steps on a bridge. It needn't be the case that you begin and end at the same point, but I think that was what people were really after, that you walk out of your home and you go traveling around, make a nice promenade through the town, and return to your home. It's fairly quick to see that you could never do that. Here's the problem. Suppose you lived on the promontory here, at the one labeled C, you'd have to leave by one of these bridges, and then eventually you'd have to come back along one of these bridges, and now you've returned home, right? And then you'd have to leave again on one of the bridges. So with 3 bridges hooking you to this the area where you live, there's no way to ever end up coming back here. But maybe you could walk around and end your tour somewhere else, maybe a church or whatever, right? There was actually a big church on the island, so that's a possibility. But Euler was able to argue that no, the walk of all 7 bridges is literally impossible. I just thought it would be fun to show you the town of Königsberg now. It's no longer called Königsberg. It's in a part of Europe that's sort of got some interesting history to it. So I wanted to show you this on Google Earth. This is the Baltic Sea, just to the north of really mainly to the north of Poland. The Baltic Sea is kind of an interesting place. It is possible to navigate through here except in the dead of winter. You enter via the North Sea, and there are 2 different straits where you can pass either through Denmark or between Denmark and Sweden and enter the Baltic. And by the way, there's 3 countries, Estonia, Latvia, and Lithuania there. Those collectively are called the Baltic states. They were part of kind of a buffer zone that was kept between the former Soviet Union and the rest of Western Europe. The Baltic states, Poland, Belarus, and Ukraine were actually part of the Soviet Union back then, so they weren't part of it. But the Czechs, Czechoslovakia used to be what that was called, Hungary, Romania, those countries were all this kind of dead zone between the Soviets and the rest of Europe. Including a big chunk of Germany. You guys are, well, I'm old enough to remember when there were 2 Germanys. Now there's just the one. Anyway, you may notice over here in the zone near the Baltics that there's this one country that doesn't have a label, and that is because it's not indeed a country. It's called an exurb, I am using the wrong word. But anyway, it's a chunk of Russia that is not connected to the rest of Russia. It's called the Kaliningrad Oblast. So you could say sort of the Kaliningrad Administrative District. And there are train lines that run into here. You can, a Russian citizen can go from the main body of Russia to here without having to go through passport control or anything. Anyway, Kaliningrad, the city, is right here, kind of near the coast. And let's zoom in on this sucker now. And we'll zoom way in. The portion, there's a port town now there, because the reason the Russians have this chunk of the Baltic area is because it gives them access to the sea. The rest of the Soviet, the Russian Federation, the ports are on the Arctic Ocean, and they're inaccessible for large portions of the year, although that may be changing with global warming. Anyway, here's the zone now that used to be the center of Königsberg, now Kaliningrad. And you'll see the Soviets tore down some of the famous Roman bridges. You can see the remnants of one of them right here just to the north of the island. And this interstate-looking thing includes the sites where 2 of the bridges used to be. There's another remnant piece right around here along the south bank of the island. I believe that's actually the site of the former bridge, although it's been replaced. Right here is another site of a former bridge. Anyway, just some fun history and the site of this thing now. I've kind of got this desire to one day visit Kaliningrad so that I could at least check out the sites of these former bridges, because it's a pretty interesting chunk of history that this really recreational math question led to discovering graph theory. Okay, so let's get on to some talking about some graph theory. There is a number associated with every vertex in a graph, and it's called its degree. Now, the one labeled 4 right here has degree 3, and so it just means there's 3 edges that leave it. If you happen to have a multi-edge situation like this one does, node 1 here, or, oh, I'm sorry, that's a synonym. You can sometimes say node if you don't like to say vertex all the time. So node or vertex 1 has 3 edges that are connected to it. We count these 2 separately. There is another option for graphs, which is sometimes you're allowed to have an edge that goes from a node to itself. So now I've made a copy of the graph that we were just looking at, and I'm calling it G3, but I have changed one thing, which is, do you see the keyword loops? I've turned it to true, and let's go ahead and look at it so you'll be convinced that I'm in fact doing the right thing. This should look just like the last thing. In fact, that's Königsberg. But what I'm going to do to that now is to add an edge that goes from vertex 1 to vertex 1. In other words, a connection from a thing to itself. And that's why I had to set the keyword, this loops equals true had to be on, because that is what's known as a loop. And let's turn it around so you can see the loop better. Now, loops are kind of interesting if you think about what's the degree of vertex 1 in this picture. Do I count this loop once or twice? Well, the standard answer is twice. What I actually generally like to imagine is you kind of cut the vertex away from the graph and then see how many stubs of edges are sticking out from it. That's how I visualize it anyway. So that the loop would connect to it in 2 different places. So it gives a degree. It adds 2 to the degree. For no other reason than just to have some fun with it, I'm going to show you a couple of other examples of graphs. This is a very famous graph called the Peterson graph, and it's not a satanic symbol, although maybe it looks a little like one. Whoops, I was trying to unzoom and I accidentally zoomed down. No, it just does that. Is it Control Shift? Oh, that's why I changed my zoom level. Okay, so there's the Peterson graph. So it's got like this ring of 5 nodes on the outside and 5 other vertices on the inside. The outside ones are connected in a cycle. The inside ones, it's connected via a star. There's a connection between outside and inside. I am not quite clear why my navigation keeps jumping around on me, but excuse me for that. Anyway, that's a cool looking graph. It's fun to kind of play around with the layout of this thing and see if you can see it in sort of other ways. For instance, one thing that would not be obvious at first, but there is actually it's kind of a 6-fold or a 3-fold symmetry to this thing, and it certainly seems to have 5-fold symmetry, but I'm not going to do it now. But you could play around with the layout and display it in an entirely different way. Here's another kind of graph that's very commonly talked about, a wheel graph. A wheel graph is a graph that has a central dot, a central vertex that's kind of a axle for the wheel, and then it'll have, let's see, I'm making a wheel graph with 15. Is this one guy in the middle and then 15 around it? No, it's a total of 15. This is the version of it where you can edit the layout. The main reason I was showing you this is that there's 2 ways to do it. P.show is, well, I'm showing the plot of the thing. I could just as well do G.show there. Don't know why I did it that way. And show of G, that's the second thing that's done here, where you get the editable layout. So it's kind of fun to play with both. This top thing is not movable. It's just an image. And what on earth? That's the thing we started with. So I've just got an extra copy of that in here. Don't know why. Oh, here's an interesting command. If you've got a graph, you can call for its edges. You can pull out the list of edges of it. And the other thing you can pull out, if you've got a graph, is its vertices. So my vertices are 0, 0, 1, 2, and 3. I guess that makes sense. My edges actually are a collection of triples, and what those triples have in them are the endpoints of the edges. So there's an edge between 0 and 1. There's also an edge between 0 and 2. Why do these things have the third element is none? That would be if there was a label. So it's possible to go in and set the labels or build it with labels intact. You can even use the labels to add colors. For instance, you can make the label be a color and then tell it to display the edges as in a rainbow pattern. All right, so I think that's a good enough introduction to what graphs look like. Let's do a little bit of theory here. So there's a number called the total degree for a graph. And the way that total degree is computed is you figure out what is the degree of every vertex in the graph, and then you add them up. So this is a sum over all the vertices in the graph, P and G. That sigma notation is maybe a little something you're a little unused to, but it basically is sigma is the Greek letter for S, and this just means sum. So often sigma notation is denoted with a range. It'll say an index starts at 1 and ends at 10, and then you would have some formula that comes after it. But you can also indicate a sum this way. All the vertices in the graph are the things over which we will sum, and we'll get the degree. So for each vertex, add up the degree. Let me do that in a real graph. Suppose I have 5 nodes, and I'm going to connect some of them. About like that. I can quickly count up what are the degrees that I see at each thing. Now, I'm not labeling the vertices. I'm noting the degree of each vertex. So there's degree 2 there. There's another degree 2. Oh, there's too many degree 2s, aren't there? So the total degree on this guy would be 4 plus 8. That's total degree T is 12. Shall we do another example? Suppose I had 6 nodes. And how about like that? Now, the particular layout of that is a little bit weird, because why would I draw this one where it's crossing over the other ones? I probably should just, if I was doing this on the computer, I could edit things and move that dot over to here. And, in fact, this graph could be drawn completely flat, and it would look kind of like a kite with a tail. I'm going to draw it like that. Oops. How long is that tail? Two edges hanging on. So you can imagine rearranging the graph so that its layout is a little nicer. That's actually a question that's common in graphs, in graph theory. This is called a planar layout, because I have drawn it flat in the plane without this kind of nonsense where something's crossing over each other. Anyway, that's not the question we were after, which was to figure out its total degree. That's a spot where you get degree 1. Here's degree 2. That's 3. And that's 3. And that's 3. And that's 2. So What is that? There's 9, 10, 11, 12, 13, 14. T equals 14. Almost off the edge. Okay, so there's a theorem that's called the Handshake theorem that tells you that the total degree is always equal to twice the number of edges. Whoops. So the sum that we were just looking at, where we look through all vertices in the graph, the degree of V, is just equal to 2 times the cardinality of the edge set. Now, actually, there's 2 sets associated with a graph. In fact, some people will say that a graph literally just consists of a pair of sets. And the 2 sets are the vertices and the edges. So I'm using what's sometimes called an abusive notation right here to say the V is in G. What's really true right there is the vertex V is in the vertex set of G. Can you tell the difference between the capital V and the lowercase v? This is a particular vertex. This is the collection of all the vertices in G. Okay. And similarly, that E of G, I probably shouldn't write it that way, but rather should say the edge set of G. Okay, so maybe I'll be more exact and re-express the theorem, the Handshake theorem, with proper notation then. It's over all the vertices in the vertex set of G, we sum the degree of that vertex. Oops, not xv. And we get twice the size of the edge set of G. Yeah. So that's an interesting result. There's a corollary to that the total degree is always going to be an even number, right? The 2 times the edge set means you're always going to get an even number. Actually, this is our second kind of name for theorems. Aside from the theorem itself, we previously talked about lemmas. That's when you have kind of a small subservient result that you use to prove something else. A corollary is kind of something that happens after rather than before a theorem. A corollary is an obvious consequence of the main theorem. So the corollary here is the total degree is always even. And that corollary actually has another corollary. So corollary, subcorollary, I don't know what to call it. A second corollary is that if you have odd degree vertices, you have to have an even number of them. Every graph has an even number of odd degree vertices. I'm going to just use shorthand here and just call them odd vertices because that makes some sense, and it feels awkward to write odd degree, but that's interesting. Now, the proof of this idea that the sum of the vertex degrees over the entire graph is twice the edge set is given in a pretty formal way in the textbook, and I think it's the second page of section 4.9. But I just want to give you the spirit of it rather than work into the... I do want to tell you what the page is, so let me check that first. Yeah, the proof of the Handshake theorem is on page 236. So what is the spirit of this? Well, it's just that if you have a graph, every time you count, if every number that you add as you're adding up the degrees gets added twice. It happens sort of at each end of an edge. So looking at another example. Suppose I draw K4 for you. I'm going to draw this in a nicer way. K4 we previously looked at on CoCalc. Looks, well, it could be readjusted to look like that. The degree of this node here is 3, and the degree of this node here is 3. If you think about this edge, I don't mean to draw a new node. That's not quite. Let's just bolden up this edge. This edge adds 1 to both of those. Does that? I hope that makes sense. That each of those 3's there includes a 1 from that edge. This guy has 1 from that edge, and it also has 1s from these other edges. The point being that each edge has 2 endpoints. Even if it's a loop, it has 2 endpoints, so it's going to add, except that they're the same. But in any case, you're going to add to that total degree twice for each loop, each regular edge. All right, so it wasn't a coincidence that our edges, our total degree came out even in each of the examples I did. Remember, there was 12 and a 14. So lastly, I'm going to go through some terminology of some standard kinds of graphs. There are sort of 3 things I want to talk about, what are known as general graphs. And that means no restrictions. You can have multiple edges, you can have loops, that's fine. Another type of graph is known as a simple graph. And that's where those sort of bells and whistles disappear. No loops in a simple graph, and also no multi-edges, or what we might call parallel edges. Finally, there's a whole category of graphs that are known as directed. Which are fun to play with. People in math tend to do this sort of thing. They can't stand long phrases, so that often gets abbreviated to digraph. In fact, not often, it's almost universally just people say digraph rather than directed graph. That means that there's some direction on the edges, as you might think. You think of them as one-way streets. So here's a very famous graph where the vertices are labeled rock, paper, and scissors. And let's see, how's it work? Rock crushes paper, and rock crushes scissors, and then scissors cuts paper. I think that's how. I'm kidding. Anyway, the direction indicates that, in fact, there's a superiority of one thing over the other, and I can't stand it. It's true that not like that. Paper covers rock. All right, so directed graphs are fun for situations where one thing is better than another, or there's an ordering implied. Simple graphs are great when a pair of things are either connected or not. No possibility of multiple edges, and you don't want to usually think about a thing being connected to itself. I mean, would you say Kevin Bacon has been in a movie by himself or with himself? That's weird. But general graphs, that's when, as often is the case, you want to allow for all the possibilities. Let's run back to CoCalc for a second, and I will end today by showing you the collection of complete graphs. So they're always denoted with a K, because I think, I'm not 100% on this, but I think the word complete in German is spelled with a K. So a lot of graph theory was started out in Germany. And so let's try making K1. Oh gosh, you have to say graphs dot. Oh, there it is, complete graph, and then give it the argument 1. Whoops, 1, not 11, and There's an annoying feature of CoCalc and Sage. Well, it's just the way it is, I suppose, that often you make a computation and it doesn't seem like you've done anything. And the problem here is that I haven't shown the graph, right? I've just done the computation. It's in memory now. I have to say show K1. Now, before I show it, don't get sad. This is going to be pretty sad, isn't it? What I'm doing is creating a graph that has one vertex and every possible connection. Yep, there it is. It's just got the one node. It's labeled 0. It's got no friends to connect to. So that. Let's change this to K2. A complete graph now with 2 nodes or 2 vertices. So we'll show it. That's really not much better. It's just a pair of things connected, right? But you get the idea. K3 is going to look like a triangle. I guess, I could save myself some typing if I just started calling these guys K. And we'll just change the number there. K3 is that. Yeah, that gets you a triangle. The layout is a little bit hard to see. But, 3 things, all possible connections are those 3 edges. Here's a good question. How many edges are there in a particular graph? K4 has 6 edges. You can count them because the total degree counts them twice, right? And each of the degrees in this guy is 3. 3 times 4 is 12, but that's double the number of edges, so 6. Or maybe you could just go 1, 2, 3, 4, 5, 6. I don't know. I just changed the layout so that the graph was given in a planar way. And you see that it's not. None of these edges are crossing at places other than that they touch each other at the vertices. I think that becomes a little harder when we get to K5. Can we change the layout of this thing so that the graph doesn't have any of these non-vertex crossings? Maybe I want to put this guy on the inside. Well, that's still no good. I don't know. What do you guys think? Could we possibly make some change to the layout so that this ended up being planar? Well, that's what's known as a fool's errand. It literally can't be done. If you try, you always have at least one extra crossing. That wasn't bad, though. I got down to just one extra crossing right there that's happening. Another famous graph that is a fool's errand, and it involves a nice puzzle that people often try to make little kids go into busy work with, is, I'll call this K33. It's called the complete bipartite graph. So let me use tab completion again and get that. Yeah, that was the first one in there. Complete bipartite graph. The arguments for here are going to be the sizes of the parts. Do you hear that bipartite sounds like it means 2 parts? Well, so I want a part of size 3 and another part of size 3. And let's show that graph too. So we actually see what's going on. It's kind of an interesting graph, and if you know the puzzle I was referring to, it's called the utilities puzzle, I think. Well, it probably goes by multiple names, but you think about these 3 graph nodes at the top that are 0, 1, and 2. Those might be electricity, phone, and water, right? And then the 3 things at the bottom, 3, 4, and 5, are 3 houses. And so the puzzle is to see if you can redraw this so that these straight lines get replaced with maybe curving arcs, but so that we don't see these extra crossings. Can you draw K33 as a planar graph, in other words? And the answer is no, but if you have a younger sibling and you want to keep them busy for a while, it's tantalizing. You feel like maybe you could do it, and it turns out, nah, it's impossible. So don't give it up. stick them on that kind of task and let them go for a while, and until they finally say, well, I don't think it's doable, and then you try to get them to ask why. But one thing you could do to try to get a planar embedding here is do something like what I just did there, but still not good enough. Still not good enough. Wait, can I do? Oh, almost. I got that one extra thing. I wonder if we can show the 3D. Oh, I'm sad. They didn't embed it properly. So K33 is actually a graph that you can see in 3D as it has a very nice geometry. It's sort of how to think about this. You think about the faces of a cube. No, I think I'm just wrong about that. The geometry of K33 is, I guess I'm thinking of K44. Sorry. Yeah. So anyway, that's another thing we could do, K44. But well, why not? Just to give you an idea of what this complete bipartite business means. Oh, I forgot to show it. There it is. This is actually the 8 corners of a cube connected if two things are sort of diagonally across a face from one another. And so it's a pretty interesting structure. Anyway, the point of bipartite is, do you notice how there's no connections between 0, 1, 2, or 3? And there's no connections between 4, 5, 6, and 7? All the connections happen between the pieces. There's even a more general situation called a multipartite graph, where again, there'd be maybe 3 or 4 different types of vertices, and the connections go between them. This kind of graph is the sort that I mentioned when I talked about airlines. The top graph, the top things could be pilots, the bottom things could be airplanes or airplane types, and the connections in this case would be, it's saying that every pilot knows how to fly every plane, but we could have sub graphs of this graph, which would indicate a more realistic situation where a pilot might know how to fly just one type of plane, or maybe 2, but not all 4. All right, so I think that's probably a good place to call it a day. We'll be working on our worksheet again in the breakout session during our class time, and I'll see you then.